So I am going to give a fairly informal talk about some aspects of stochasticity and what it does for understanding of magnetized turbulence, which is a surprisingly contentious field long after our views of hydrodynamic turbulence have converged. There are a lot of outliers in this area and with varying relationships to reality. So I'm going to give a fairly personal tour of what I think is going on and what stochasticity means for it. So I have a bunch of collaborators to thank, and I've left some of them off because I ran out of time to think of them all. Anyhow, so I'm not sure whether or not you all have a background in turbulence, and I know Greg has just given a fairly high-level run through, but let me mention a few issues here which feed into our understanding of magnetized turbulence. You know that people have described turbulence qualitatively for roughly 500 years, at least that we know about. This is a page from a notebook by Leonardo da Vinci. He worked on this problem for about 5 years and grasped the idea that there were large-scale structures and small-scale structures, and something very complicated was going on. But of course, we didn't arrive to a modern understanding of turbulence, even approximately until fairly recently, before I was born, but still fairly recently. This is a rough schematic of what Kolmogorov worked out in 1941, where looking in Fourier space now and viewing the flow of energy through phase space from large scales to small scales and then on to dissipation, he sketched out the power spectrum that we expect to see with a stirring scale, large scale stochastic effects of the stirring scale, a flow of energy from this peak down toward the right, and eventually to dissipation. And this forms the basis for the discussion that's gone on ever since then. Now, right at this level, we see that there's all kinds of interesting things going on, and Greg touched upon the most important one, which is to say, if you consider trajectories through this fluid, if you make a three-dimensional model, say, of the flow lines, freeze them at one point, and then follow them along, you see that they follow a complicated pattern, but that any two trajectories that start close to one another diverge rapidly, roughly an eddy. Their separation will grow by an eddy scale for every length of eddy that they go, and they're sampling larger and larger eddies. Of course, this is not the way actual fluid elements move, because the turbulence itself evolves, but the evolution in time still shares that basic characteristic that you see a linear divergence in their separation as a function of distance traveled, which is not the same thing as time because the velocities change. And this is anomalous or Richardson diffusion, and we've known about this for almost 100 years now. What's not often appreciated, or at least was neglected in my education, was that not only is this faster than normal diffusion, but it is qualitatively different from exponential divergence, which is often thought of as the default case. In an idealized cascade, you get stochastic evolution. That is to say, trajectories can start at zero separation in an idealized system and become large in a finite time. So from the point of view of determinism, this has two aspects. One is that the average distribution of particles becomes smooth, which in a sense, you can think of as a triumph of determinism. Everything gets washed out. Perfume is equally noticeable at all points in the room. Smoke fills a volume. Your cream is diffused through your coffee cup, although most people don't stir by creating chaotic patterns, but okay. But if you are interested in the trajectory of any particular particle, which is exciting for some reason, say it's a forest fire and it's a burning ember, or it's astrophysics and it's a high energy clump of particles, then you've lost predictability. And things that start out very well defined immediately become unpredictable. And this, by the way, has some practical applications, which I'll mention in a few minutes before I end the talk. So intellectually, it seems like a natural step to go from fluid turbulence to magnetized turbulence. And it's slightly complicated by the fact that magnetized turbulence is really virtually non-existent in terrestrial contexts, but extremely common in the universe. So in astrophysics, we almost always want to talk about magnetized turbulence, but we don't have an experimental base experience to refer back to. Just a few examples here. The convection zones of stars, where the convection is driven by an unstable entropy gradient, and it's important for the outward transport of energy. It is also, by the way, important for the generation of large-scale magnetic fields by stars. Accretion disks around black holes or stars, there the instability is driven in an ionized plasma by the embedded magnetic fields and the gradient of the angular velocity, which leads to an outward transport of angular momentum and an inward transport of plasma, resulting in very high energy phenomena visible across the entire universe in some cases. The interstellar medium, which is driven by multiple mechanisms, and people will argue about which one is most important, but there's an impulsive energy generation from supernovae and other stellar explosions. There are winds from high mass stars and low mass stars. There are magnetic instabilities, there are gravitational instabilities. Somehow, all of this produces something that looks remarkably similar to Kolmogorov turbulence in the interstellar medium. And we have the solar wind, where we see turbulence in the wind as it blows by us, which seems to be fed by the energy of embedded magnetic structures that are imprinted as the wind gets blown off the sun, and then decay and drive the turbulence. So what does it look like? There's a long history of arguments about how this works exactly, but the critical ingredients that I think most people would agree on now is that magnetic fields support waves. The magnetic fields are like strings, you pluck them, a wave runs along, and the Alfvén waves have a characteristic frequency proportional to the parallel wave number, and insensitive to the perpendicular wave number. And Goldreich and Sridhar proposed that the way to understand what's going on is that there's a critical balance condition, which describes the turbulent cascade, where the nonlinear interaction rate is held similar to the wave frequency. The mechanism that enforces this is frankly a little obscure. I think it does emerge from sort of lowest order energy interaction models, but it emerges because that's sort of a stationary point. If you like, you can think of it that when the magnetic field is negligible because the parallel wave number is too small, then the dynamics are like fluid turbulence, and it will evolve toward isotropy. If the parallel wave number is too large for this condition, you'll just have a bunch of waves running around, and they tend to decay with constant parallel wave number in the direction of higher and higher perpendicular wave numbers until you satisfy the critical balance. So what this means is that you get eddies that are strongly anisotropic and become increasingly elongated along the field lines at smaller scales. But the overall power spectrum probably has the same index as Kolmogorov. There's a little bit of, well, there's considerable argument about how close to Kolmogorov it is, but that's the general idea, and it works out something like that. Numerical simulations, originally by myself and a student, Cho, also by Jason Marone and Peter Goldreich, showed that this picture is broadly correct, but it shows some funny features, which people are still arguing about. There's stronger magnetic field intermittency. The velocity field intermittency looks very much like Kolmogorov, the hydrodynamic case, but the magnetic field intermittency is much stronger. And it's noticeable even qualitatively if you look at pictures. And then there's possibility that you get spontaneous polarization of the eddies in local regions so that the waves tend to line up. And the degree to which that increases as you go to higher wave number is subject to strong arguments. So the analog to Richardson diffusion still works, except that the principle that trajectories separate by one eddy width as they go one eddy length means that since eddy lengths are now long, the process is quantitatively slower, but still linear in distance traveled. Now, why is this important? Just to put up the simplest version of the induction equation, dB dt is, the curl of the electric field, minus the electric field. If you write this out in the MHD limit, your first term is the usual ideal MHD law, and then you have a resistive term, which is generally taken to be small. Certainly the resistivity that enters into that term is small compared to the natural dimensions of the system, although the gradient of the current diverges as you go to small scales, so you can get interesting effects. Anyhow, if we imagine that the resistivity is exactly 0, which people do at the beginning of every semester in every class on MHD that's taught in physics and astronomy departments, you conclude that you have flux freezing. The magnetic flux through a fluid element cannot change in time. Magnetic field lines are tied to the fluid elements and vice versa. They are unbreakable threads, and people quote this result and move on, but this is actually grossly inconsistent with what we see both in nature and in numerical simulations. So I have a little movie here where you see X-ray picture of the sun, and there are all these bright spots varying in time, and pow, that one just went off in the middle of the picture. That was a whole bunch of magnetic field lines reconnecting over a significant volume in a brief moment in time. Big burst of X-rays, highly energetic charged particles. Lovely to watch. Not so good to be downstream of. Let's move on. Okay, so what's going on here? So in the 1950s, Sweet and Parker independently worked out how reconnection could occur if you had a very small resistivity. The idea was that you squeeze together magnetic field lines of opposite polarity, and then you diffuse, you annihilate the opposing components of the magnetic field, because resistivity can be strong in this narrow little channel, and then the plasma that's entrained on these field lines is squeezed out at the ends because it has to move along field lines. So the width of this zone is set by the resistivity. Contrast that with this picture below it, where we have put in some realistic amount of turbulence, not even very strong. The field lines all wander a little bit. And now if somewhere in this zone, some plasma is involved in a reconnection event, it follows magnetic field lines out the end, but it's now wandering in a turbulent diffusion way, and you get a broader outflow zone. So whereas in the top picture, the Sweet-Parker model, the width is set by resistivity, in the bottom one, it's set by turbulent diffusion. It's stochastic diffusion. And this is the model by Lazarian and some other guy in 1999, which describes the whole process as being limited basically by turbulence, which we referred to it as stochastic reconnection rather than turbulent reconnection because there was an entirely different and physically unreasonable model of how turbulence might cause reconnection that preceded us by a few decades. And we were trying to avoid the connection. But it is also true that this is stochastic in the sense that it relies upon the stochastic trajectories in the turbulence. So we made this prediction and people gave us crap. So we tested it. A few years later, we got someone who actually knew how to do numerics. And this is an intrinsically three-dimensional simulation. We had to have the right kind of outflow conditions so stuff could stream out the ends of the box and fresh magnetic flux could gradually move in from the top and bottom. And Grzegorz Kowal was the numericist on this project. And so we tested the reconnection speed in a environment with a set level of turbulence and varied the resistivity. And we got this lovely graph here where the reconnection speed in the Sweet-Parker model without turbulence is depending on the square root of the resistivity. So that's this curve here on a log-log plot. And as long as we keep the turbulent environment at a constant level, this is the reconnection speed that we expect. And this is what, in fact, we got. So you can get a sense of how the two models differ just by looking at these two diagrams at the bottom, where on the left, this is actually from Kowal's simulation before he turned on turbulent driving. And on the right, this is the same current sheet, but now being buffeted by fairly strong turbulence. So this was a great success. And then we varied the power of the turbulence and left the resistivity constant. And now we see we get an increase in the reconnection speed as expected, while the reconnection rate before we turn on the turbulence is, of course, constant. And we had two different guide fields, that is to say, magnetic fields coming out of the screen, which, as expected, had no particular effect on what we were doing. So, of course, having demonstrated that this all worked, we were immediately accepted by the plasma physics community as being right about the effect of turbulence on reconnection. Sorry, just kidding. There remains a touchy point. I'm not going to try to explain why. I'm satisfied we're right. Anyhow, so as a follow-up work, this is from a PRL letter with Lalescu et al., including both Greg and myself and some other people. We took a look at a turbulence simulation that's online. In fact, it's still online, being hosted here at Johns Hopkins. It's a simulation of incompressible MHD turbulence, driven MHD turbulence. And we just picked out regions that looked interesting and binned them closely and then loosely to see what they looked like and if we could identify reconnection zones. And here is something that kind of looks like a mess if you look microscopically. But if you bin it more crudely, you see a nice magnetic surface here. And here's something that looks like an X-point reconnection going on. And it all looks like there's smooth dynamics with a greatly enhanced reconnection rate. But it's actually this mess here on the left. And this shows you the power of binning to confuse you and think that something nice and smooth is going on. So work on this has gone on. There's been some very interesting work based partly on an idea by my collaborator Lazarian and followed through by his former student Vishniac, but then many other people looked at this, that show that if you don't have a turbulent environment at all, you just have a case where magnetic fields of opposite polarity have been pressed tightly together, that this spontaneously develops instabilities. In fact, qualitatively, it looks a lot like the shearing instability that Greg showed you in the last talk. It drives instabilities, and people argue about the relative kinds of instabilities being driven here, but you develop a zone, a turbulent zone, and I don't mean that just figuratively that it looks like turbulence. I mean, if you analyze the zone, it looks like driven turbulence numerically. And you just automatically reach reconnection speeds that are a few percent of the Alfvén speeds. That is the characteristic magnetic speed of the environment. So what all this tells you is that reconnection in a turbulent environment is rapid and omnipresent. In an environment where turbulence fills the whole space, you expect that it'll be somewhat intermittent, but so rapid that it'll be difficult to store large amounts of excess energy in the magnetic field and release them suddenly. You tend to get a web of reconnection events going off one after another with a fluctuating overall energy release rate. Not only is the magnetic flux freezing broken by the presence of these reconnection events, but in general, and this is also something you can see in the turbulence database at Hopkins, the magnetic field lines have no unique identity in time. That is to say, you can take a fluid element, you can draw the magnetic field lines through it, you can extend them out to the ends of the box. You can do that throughout the box. You get this nice map of magnetic field lines. You can step forward in time and do the same procedure, and you will get a different set of magnetic field lines because there have been so many reconnection events everywhere that it is not physically meaningful to speak of a magnetic field line. So that raises the question of why people ever do speak of magnetic field lines as dynamic entities. And I'm going to show you a picture in a minute, but there's a clue offered by the fact that if you have a quiet environment, then magnetic reconnection is going to be intermittent. There's going to be the formation of current sheets, the growth of the instability in the current sheet, and then rapid reconnection. And then things will relax for a while, and you will go back to building up sharp current sheets. And if you take magnetic field lines in a turbulent environment and you eject them into a quieter environment, you'll see some very amusing things which illustrate the random stochastic nature of the particle trajectories and the heating. So let me show you, and I will end with this picture. Here we go. This is an illustration of why people like to talk about magnetic field lines. Here we have a picture of a solar prominence, and down below is the photosphere of the sun. I think this is an H alpha. Anyhow, it's in a spectral line, so the whole thing becomes manageable and visible, highly illuminated at certain points. So here you see a carpet of magnetic field lines, and there's all kinds of reconnection events and so on going on. But some of the field lines have been lofted outward, and there's plasma contained in them. And this gives the illusion that there are threads of magnetic field lines separated from others. And it's not really true. There are magnetic fields filling this whole volume, but some of them have really hot particles coursing along them, and some of them don't. So you're illuminating a random set of trajectories, and it produces this amazing thread-like experience, because what's happened is you've taken these complicated field lines and you've stuck them in a quieter environment, and the rapid expansion and the quiet environment has greatly reduced the kinetic temperature of the fluctuations, the turbulence along the field lines. And suddenly you see all these threads that look nicely defined. Now, they won't stay that way forever, but this is a dynamic, evolving phenomenon, so it doesn't have to stay that way forever. Okay, I will mention one last thing, which is that people who study these kinds of events get funded partly for the purpose of predicting when you'll get a really big one. And the problem with this is that this actually is like the weather, and you can predict hurricane season, but predicting hurricanes is extremely hard because of the butterfly effect. So you see these things erupt. Well, some of them are very big, and some of them are going to hit the Earth. And when they do, sometimes a power grid goes down. And if we are very unlucky, all the power grids will go down. But we haven't been hit by one of that strength for about 150 years. It's hard to judge from the records, but probably the one before that was 100 years earlier. People say that because you could see the aurora borealis from the Caribbean in the 18th century when this happened. In the 19th century, you could see the aurora borealis from the Caribbean. And also, all the telegraph wires were self-powered for the duration of the flare. If those had been a power grid, they would have burned out all the transformers. So my understanding is that the plan, when this happens to us next, and I won't say we're overdue because it is a stochastic event, when it happens to us next, the plan is that the government has a stockpile of transformers. We hope they do. That's actually, I think that's classified. And our recovery will depend on how fast you can replace every transformer in the North American power grid. The same comments go for Europe, where I know even less about what preparations might be made. There have been worse flares, but we don't know much about them. They're recorded in things like isotope variations. And it might be that the ones we've seen in modern history aren't nearly as big as they can be. And I think the bad news for the funding agencies is that these are inherently unpredictable events. Okay, end of talk. As soon as I can find the off button.
Thank you.
One of these off buttons is live.
Well, we definitely have some
There we
time
go.
for questions, both for Ethan talk and for Greg talk. So also people online, of course. But well, so we are all a bit tired. But if there are questions, you know, exactly. I just said. No, go to Greg and to Ethan. So okay. Nicola?
Okay, yeah, so thank you very much for these two fascinating talks. I just want to make sure my understanding is about correct. Let's say try to summarize my, only partial understanding. So I knew already about the Norton's dome, which is fascinating, but which is quite contrived because this potential has to be exactly the way it is according to this Northern dome. And also the initial condition has to be precisely at the top of this dome. So I thought it's a nice illustration, but it's not very, well, it's not going to happen in reality, let's say. And so what you are telling us, okay, but tell me if I'm correct, is that actually it is very contrived example exists almost everywhere if we go to all kind of fluids. It's not at all that contrived, it's a kind of standard that is in these kind of more complex systems. It happens everywhere all the time. Okay,
Yes.
yeah, I see from your heads that you're already agreeing. Okay, that's really fascinating because so yeah, Newtonian mechanics is deeply non-local, not non-local, non-deterministic. Thank you very much. Excellent.
By the way, I mean, I just mentioned in context to that is that, I mean, there's the rigorous mathematical work on this has all been done within classical mathematics. but it should be possible to also study this intuitionistically. And my argument for that is that we can see all of this in numerical simulations with finite precision arithmetic. And
Yeah,
so,
yeah, I'm sure you can do that also. It's
yes.
even probably more natural, and maybe it's saving a bit of computer memory, or maybe it could be a bit faster.
Yeah, but
Greg, have you got any numerical simulations that are infinite precision?
oh, of course not. Nobody does. Well, I mean, I guess
you were so keen to. I really.
I was simply saying that, of course.
Oh no! I think
No, I
you
mean,
have
of course,
something.
I mean, of course, we were not going to the same kind of precision as Charda was with his 3-body simulations. We were at most going to standard double precision. We didn't even have to go to quadruple. And I guess I was simply trying to emphasize that all the phenomenon can be observed. Of course, you can't prove it, but you can observe the essential phenomenon in numerical simulations with no real singularities and with finite precision.
Yes.
So
okay, I have because I'm a bit noisy. If you could read the chat.
yes.
To see if I'm correct in that, and then I'm going to put something on the numerical simulation effect of SS. 1 second.
So were these questions?
Oh, this is just vague speculation.
Well, I mean, so first of all, I mean, I agree that Navier-Stokes equation is incomplete. And in fact, this is separate work that we have done.
Classically.
Yeah,
classically complete.
Yes, I mean, in fact, I mean, it's wrong already at millimeter scales, but this is really separate because even if classical deterministic Navier-Stokes were correct, you would still see spontaneous stochasticity coming from any small environmental noise. But I guess the point of our recent work is that that description in terms of deterministic Navier-Stokes is physically invalid because, first of all, it's inconsistent with the fluctuation dissipation relation, and you never in nature have dissipation without fluctuations. And if you put in those inevitable thermal fluctuations, then you can never get rid of the stochasticity. And in principle, it's not possible to have a single deterministic solution because that random thermal noise, which is inevitable, will always propagate to the large scale. So that was the point of the thermal noise, although even without it, mathematically, we still expect that deterministic Navier-Stokes would evidence this phenomenon of spontaneous stochasticity, but now you would have to have some other source of noise. You know, could be butterflies or microorganisms or, you know, whatever other kind of environmental noise there is.
So you're saying that if the Navier-Stokes was a perfect classical description, you would still need a source of noise?
Well, so in spontaneous stochasticity, as it's currently understood, there's always some external source of noise that could be some added random noise that's either quantum or thermal, or it's randomness in the initial data. And within the classical, the mathematical description, spontaneous stochasticity is simply a magnifier of that noise. It's not something that produces the noise intrinsically. It's just it's an incredibly stronger magnifier than classical chaos, which, you know, has a finite rate of amplification. In spontaneous stochasticity, you have an infinite rate of magnification. So, but that's all within sort of the classical description. So,
I'm sorry to insist, I really want to probe your mind. So the quantum noise would be on its own enough, but you'd still need a thermal, some kind of classical microscopic thermal noise.
No. The quantum is sufficient by itself to produce spontaneous stochasticity. You don't need thermal noise. That we can prove mathematically. In fact, I originally got interested in this question of quantum spontaneous stochasticity precisely because it was so frustratingly difficult to see spontaneous stochasticity in laboratory experiments. And I thought, well, maybe it would be easier in a tabletop experiment with quantum systems. I talked to Ketterle's group at MIT about that, and they started smiling when I described the kind of experiments that would be necessary. I guess the problem is that it's sort of intrinsic in spontaneous stochasticity that you don't remember the source of noise. And in fact, what you see in the random output is essentially the same, whether the origin of the noise is quantum or thermal, it doesn't matter. If you really wanted to show quantum spontaneous stochasticity, you would have to go to incredibly low temperatures so that you could be sure that there was no other source of noise than the quantum noise, but there would be no other special signature that it was quantum in origin.
You have found a problem more difficult than the quantum computing problem.
Oh, yeah, okay, well, that wasn't my ambition, but I think that the good news is that you should be able to see spontaneous stochasticity. In fact, I mean, I don't think it's that hard to see it in the laboratory because you could simply build an analog of the Norton dome. I mean, if you want to see it experimentally, we could, and you just build a Norton dome and you put in some noise and you take the appropriate limits, and I'm sure that we'll see it because we can derive it analytically. And so I think we can definitely show that there's spontaneous stochasticity possible. I think the more interesting question is, does it happen naturally in the real world and relate to important, interesting things that we're already seeing, like magnetic reconnection and rapid transport of passive scalars in a turbulent flow and phenomena like that, drag behind your car when you're driving down the road. So that's been much harder to verify.
If nobody has a question, I'd like to know the name of your MIT colleague.
Yeah, okay, so we have.
Post a question is probably, you know, as soon as you mentioned Norton's dome, I thought, okay, now I know what's going on. But in that case, of course, you have no noise, and also in that case, it's really a set of measure zero conditions, which means you're not worried about violating Lugos theorem, right? Because it's going to be zero in and zero out. But if it's really generic, then how does this fit with Lugos theorem? It sort of seems as though the volume, you know, if I take a volume of the phase space, it's just not going to remain constant if this sort of thing is happening.
Well, first of all, for the Euler equation, which is the simplest case where we see this should happen experimentally, I mean, it's Hamiltonian, but it's not canonical Hamiltonian. And the phase space is infinite dimensional, so you don't really have a Liouville theorem anyway. The actual fluid equations are described by Navier-Stokes, in which there's no Liouville theorem either, or Landau-Lifshitz equations. They don't satisfy a Liouville theorem. They satisfy an analog of it, but I mean, so there's a fluctuation dissipation relation. There's a Gibbs measure. Those all are features that are related to the Liouville theorem, but you don't really have a Liouville theorem in nature for those phenomenological models. Those are hydrodynamic descriptions. They don't have a Liouville theorem. But what we do know, what was predicted by Onsager, and which is amply verified by experiment, is that in the high Reynolds number limit, you see rough velocity fields everywhere. Not at one point. Every point in a turbulent flow is rough. It's got Holder exponent less than 1. Now, this has to be understood carefully. The actual velocity field in some sense is smooth. It only appears to be rough over a long range of scales, the so-called inertial range. And then you effectively have a Holder exponent of around 1/3. And it turns out that's enough. You don't need actual singularities. That's the main difference with the philosophical example of Norton's dome. You don't need actual singularities for these phenomena to occur. You only need quasi-singularities. And so this is what happens in a turbulent flow. So I mean, I have a nice, if you look in my paper on the RG theory with Dima Bandek, we have a nice plot of this. We show a phase diagram. So it's very similar to what you see in quantum critical phenomenon. And that is, if you let the external noise get very strong, you don't see spontaneous stochasticity. You just see the external noise. If you let the external noise get really, really weak, then you actually see deterministic behavior, but it has to be super exponentially weak. But then there's this whole broad range of the phase diagram where you don't require real singularity, you don't require real zero noise, but what you see is spontaneous statistics that correspond to infinite Reynolds number and zero noise. Just like you don't see, quantum phase transitions happen at zero temperature. You never really get to zero temperature. The reason that you see the effects of a quantum phase transition is because those effects are seen at finite temperatures. And so the same thing is true for spontaneous stochasticity. You don't have to go to infinite Reynolds number to see those effects. You see them at sufficiently large, but finite Reynolds numbers, sufficiently low, but finite external noise. And then the phenomena predicted in the Norton dome is actually what happens. And that's what you see.
Okay, thanks.
Yeah, well, so Ethan said something that about how Richardson diffusion is tied, at least conceptually, to eddies, which I didn't know before, and it was interesting to hear. I was wondering how generically spontaneous stochasticity is linked to something like eddies.
I couldn't hear that question, sorry.
Oh,
Ethan, did
yeah.
you get
I didn't. I was hoping you did.
it was very garbled, sorry. Maybe you could type it.
So this one,
Yeah, you have to go.
so
With your hands.
I was wondering, I was wondering how related spontaneous stochasticity generally is to eddies and persistent structures in the fluid.
Well, I mean, I don't know how to answer that question. I mean, of course, it is I mean, I'm not sure exactly what the question is. I mean, of course, the phenomenon of Eulerian spontaneous stochasticity is due to the eddies sort of evolving in this random way. And so you get this propagation of the random perturbations from small scales to large scales. I mean, are you asking whether spontaneous stochasticity violates the idea that there are persistent structures? Because it doesn't. And of course, as was made in several comments of the previous talk, like Gissen's, I mean, is you could have a number which is only partially random, like you would take, every odd digit would be coming from pi, and then every even digit would be from totally random number generator. And so generally in a turbulent flow, you have a mixture of things that are purely random with things that are almost very predictable. So you have very long-lived coherent structures, and these things coexist.
Yeah, it's particularly true for magnetized turbulence,
Yes.
where you don't even have to look at the eddies. You can look at these clumps of magnetic energy which form and persist for long periods of time. But nevertheless, they're multiply connected to the environment, and those connections shift constantly.
Okay, thanks.
I mean, another example would be even in a totally random process, like Brownian motion, there are some things that are almost sure. Like you can say, I have almost surely a Holder exponent 1/2 minus epsilon. And so the fact that something is totally random doesn't mean that there are not some things that are entirely predictable. And so in general, in nature, we see a mixture of these things, and some things in a turbulent flow are highly predictable, while others are totally impossible to predict.
Did you mention, Greg, that the two articles by Lorentz in 1960, one of 69 and one of earlier, the one was more close to spontaneous stochasticity and
Yeah,
the other
this-
one was more the butterfly?
Yes, that's right. I mean, the 69 paper is in some ways the vastly more revolutionary of the two papers. And it's interesting that, you know, Lorentz is mainly remembered for his 63 paper, and yet the 69 paper is a much more profound and revolutionary work. And I think Tim
Yeah.
Palmer has been advertising that correctly, that people should be paying a lot of attention to the 69 paper.
Oh, I just had lunch with him last week, and he never heard of spontaneous stochasticity.
Well, that's okay. That's fine. I guess we've heard of him, you know, so the people that are you know, so I think that this connection between Lorentz's work and spontaneous stochasticity is relatively new. And the first person I think that made this connection was Alexei Malyabov in some work that he did in 2016. And I would say that now, I mean, this idea of, I would say one of the reasons that Lorentz's work has not been appreciated was that, unlike chaos, where mathematicians jumped in and they very quickly understood the mathematical underpinnings of Lorentz's 63 paper, the underpinnings of Lorentz's 1969 paper have been very obscure. And although Lorentz in the 69 paper had all the correct intuition, he had no idea how to implement this mathematically. And I think that we now, and I don't know that Palmer would even agree with this, I would say we now understand that the correct mathematics behind Lorentz's work is in fact spontaneous stochasticity and associated with the non-uniqueness of the limiting solutions of the high Reynolds number equations. And I don't know that, I've never seen Palmer write about that. I don't know that he would even agree with it, but I would argue that in fact, that is the way that you understand correctly the mathematical formulation of Lorentz's idea. It's in that precise limit that you get a deterministic equation with random solutions. It's when you take, for example, the high Reynolds number limit of a turbulent flow, the singular limiting equation is Euler equations. It's a deterministic equation, but the solutions are random. And that's because the Cauchy initial value problem for that equation is formally indeterminate. There are non-unique solutions. And so what you end up with is getting
article of Lorentz compared with the comment by Onsager that was earlier.
Well, Onsager, interestingly enough, never commented specifically about anything that I know of related to spontaneous stochasticity. He did in his 1949 paper mention Richardson dispersion. He did in that paper point out that you have Holder exponents less than 1/3. I don't know if he ever connected the two. And I mean, I'm sure he knew about the non-uniqueness phenomenon for differential equations. He was a very good mathematician. Although he was professionally a chemist, he was a brilliant mathematician. And I'm sure he's aware of this, but I'm not I don't know that he ever connected this. I wouldn't be surprised if he had, because I went into his notes and I found very surprising things. You know, like he understood that the Dirac equation applied to graphene back in the 1950s, and all kinds of amazing stuff is in his unpublished lecture notes. And so it's very possible he understood these things, but I don't know of any writing that he, you know, in which he stated such a thing. And so I think that that's why I really give great credit to Krzysztof Gawedzki, and I think, and his collaborators, but especially Krzysztof, who were the first people to really understand sort of the origin of this indeterminacy in the non-unique solutions of the limiting singular equation, and the fact that in that appropriate limit, you could get a random distribution on those non-unique solutions. And he understood, I mean, the first time I talked with him was at IHES in 1997 about this. And I had been working on the problem of anomalous dissipation for passive scalars. And the first time I met him and I talked with him for an hour, I said, he understood this much, much more deeply than I had. And I became an immediate, advocate of this idea. I mean, he convinced me. And I think it was a brilliant idea that makes close connections with things like Parisi's work on replica symmetry breaking. It has lots of deep mathematical connections. And I think that it gives to me the correct foundation for Lorentz's work. And of course, that's still a very controversial statement, but I think we'll see how this develops in the future. But certainly what we see in the numerical simulation that I showed you, we see clear evidence of what's now called spontaneous stochasticity, and it's clearly by Lorentz's mechanism. It's that inverse error cascade from small scales to large scales. And so at the very least, you could say one way is that Lorentz's mechanism sort of implies spontaneous stochasticity, but also the specific statements he's making about formally deterministic solutions behaving indeterministically only becomes a sharp statement if you look at the infinite Reynolds number limit, and then you get deterministic Euler equations. I mean, this doesn't apply to, like deterministic Navier-Stokes. Well, that's another issue. There may be non-unique solutions of deterministic Navier-Stokes as well, and that's part of the Clay Millennium Prize problem. But I would argue that that's a pure math problem, not a physics problem, whereas this is real physics. But anyway.
Thank you.